Welcome back, everyone. Let us please welcome Professor Renato Pessoa Vale. So Renato is currently professor at the Federal University of Goiás, where he also graduated and defended his master thesis. His PhD was defended in Unicamp, and he worked in a postdoc project at the University of Arizona. His current research interest involves mainly solid helium and simulations of ultra-cold fermionic gases.
Hello. Hi, everybody. Can you hear me? Okay. Hello, everybody. Thank you. And first of all, thank you for the invitation. I'm so glad to be here and give my contribution for this São Paulo School of Advanced Quantum Fluids. Thank you very much for the invitation. Today, I will talk to you about the quantum Monte Carlo simulation of a polaron in the unitary Fermi gas. It's a term that has many interests of the experimental point of view, and also for theoretical point of view. Then I will talk to you about this methodology and how we can to simulate this polaron in a Fermi gas in the unitary limit. Okay, basically we consider the strongly interacting unitary Fermi gas where the scattering length goes to infinity. And I will talk quickly about the scattering length, the definition, and the importance to study this regime. And after this, I will explain about we will use the fixed node diffusion Monte Carlo to study the ground state properties of basically two different systems. A system we formed by any particles plus N1 impurity, and the system formed by any particles that we call bath, and M impurities in the system. Then with studying these problems, we can use a model to describe the polaron that I will explain to you. Okay. To model the interaction between the particles, we use the square well potential. We employ this in the simulation and calculate the polaron properties as a function of the potential range. Well, for this finite potential, we have well defined the range of the potential, and the properties that you calculate in your simulation is very affected by this potential range. After this, or besides that, we apply the Wigner-Pires boundary conditions to implement a zero-range potential model. I think that this part is that we have like a new thing in the area, because we can do the Monte Carlo simulation implementing a model that we don't depend of the range potential, that we can get the properties of the polaron or anything we want without an extrapolation. Because in principle, you have to make some extrapolation doing the range of the potential small than you can. Okay, and we verify the impact of the range potential in the calculation of polaron properties in the unitary Fermi gas. For example, the binding energy, the effective mass, and other properties of the polaron. Okay. Okay. In this moment, I will talk to you about the basic things about the systems. I think that the first thing you have to talk to you is about the fermions, and the difference between the fermion system and the boson systems. Basically, for boson systems, you have particles with integer spin. And in this case, we can put all the particles in the same quantum state or in the ground state, and you can have a condensate. It's I think that a point of view of the physics, the mechanism is more simple than the fermions. For fermions systems, we have a difference. And the main difference is in this case, we have half integer spin. Then you cannot put the two particles in the same quantum state in your system. You have to fill the energy levels. You're putting two particles in each level, no? And you can define a down spin and an up spin, and you can fill these levels until the last level, depends on the number of spins you have. This last level is called the level of Fermi, or Fermi level. And for this last level, you can define the Fermi energy and the momentum of Fermi. Then, basically, for a system with some density, you can write the Fermi energy like this expression, where this part is the momentum of Fermi squared. And it's very simple. But if you have a unpolarized Fermi gas, I mean a Fermi gas with the same number of spin particles and the same number of the same number of down spin particles and up spin particles, without the interaction, you can write the energy of this gas like this expression. 3/5 multiplied by the energy of Fermi. Okay, for the fully polarized case, is a little bit different. Because if you have the Fermi particles with the same spin, for example, the particles with up spins, for example, but could be down spins, the energy of Fermi is defined by this expression. It's a little bit different from the another case. But also in this case, the energy of the gas can be obtained like 3/5 multiplied by this energy of Fermi. And also in this case, the momentum of Fermi is defined by this expression. Okay. This is just the basic things we have to remember to study the gas we want. Okay. Now, about the problem we want to calculate. Basically, the polaron can be observed in the gas if you can put an impurity represented in this figure by this blue symbol, this blue diamond. When you put this impurity in the bath, the impurity and your neighbor can behave like a quasi-particle. In other words, the excitation spectrum of a slow Fermi polaron behaves as a quasi-particle of an effective mass m star that you can obtain by this expression, where delta E is the difference of energy between the system with the impurity and the energy of the bath. Once you can calculate the energy of the bath and the system formed by the bath and the impurity, you can obtain the excitation spectrum for the polaron. Then what you have to do is to put this impurity in different momentum states and observe the behavior of delta E. Okay, in this expression, you can see you have the first term that's like a kinetic term, and the second term is the binding energy of the polar. Then, in this work, we can obtain this effective mass and this term A that's associated with the binding energy. In principle, you can put everything you want for the bath. But in our case, maybe it's the simple than that. You put the bath formed by N fermions with up spins, and the impurity is another fermion with the same mass, but with down spin. It's really, really simple. Well, if you want to observe the behavior of the interaction of different polarons, you can do that putting 2 or 3 or more impurities in the bath. You can do that if you construct a system formed by this. The energy of the system can be modeled by the Landau-Pomeranchuk model, where we have a concentration of impurities given by X, where X is the any down particles for our case, over any up particles that form the bath. And the energy for this case is given by this equation 4. Then basically we have the A parameter, the effective mass, and another term that take account the interaction between the polarons, this F term. Then if you calculate the energy for different concentrations of impurities, you can obtain this interaction between the polarons. The first paper that obtained these properties for using Monte Carlo simulation was the paper of Carlos Lobo and co-workers, 2006, where they calculate the energy using fixed node diffusion Monte Carlo as a function of the concentration. They can fit some curve and obtain the properties of the polaron. Okay, now we have to understand what means the unitary limit, because in principle you can do the same thing for different scattering lengths for the gas, but in this case we are interested in the unitary limit. Then the beginning is the two identical fermions interaction via spherically symmetrical potential. In this case, we can write the two-body problem like this equation, the Schrödinger equation, and the solution can be written with two parts, where you can see a radial part and another, the angular part is basically polynomial form. The radial part can be used to define this U function that obey an equation like this. It's similar on Schrödinger equation for two-body, just for the radial part. Okay. Another thing that you can note in this case is in the limit where the range of the interatomic potential is much smaller than the relative distance between the particles. For this situation, the radial part of the solution of the wave function is proportional this sign of this term, where delta 0 is the phase shift, and k is the wave function of the scattering wave. Okay. Today in the morning, Professor Tomillo told us about the quantum scattering with many details, and it was really good. But I will not show you all the details about the scattering theory. In this case, the scattering amplitude can be obtained and the expression is something like that, the equation 9. It's a function of the wave vector of the scattering wave. In the limit where the k goes to 0, the scattering amplitude goes to minus a, and a is a constant value defined and called by scattering length. Basically, it's this. A is the scattering length defined with the scattering amplitude. Okay. In that expression, when we expand the phase shift at low moment, including terms to order Q-squared, the scattering amplitude results this. And this is very important because we can see that the scattering amplitude depends on the range of the potential that we are considering. But we can restrict our analysis considering two different characteristics. For example, the limit where the scattering length goes to infinity, that we call unitary limit. In this case, the 1 over a, this term disappears. And for the case where the range of the potential goes to 0, this term in the denominator goes to 0 as well. And the scattering amplitude has this form. Then, because the scattering amplitude doesn't depend on the characteristics of the potential, the system, in this case of the zero range potential, has universal behavior. And the properties don't depend on the potential details. Then you can use which potential you want. And if the range goes to 0, the properties doesn't depend on the potential. This is a very characteristic. Okay, it's in a theoretical point of view is a little bit simple, but it's not so simple to do a simulation in the computer because you have to put a model of potential, and most of people do that, putting a kind of model and checking the behavior of the properties as a function of the range potential, and make some extrapolation in some moment. And we are doing this in this work is different. We have a way to avoid the extrapolation of the potential. Okay. For the problem with many body particles, to consider that characteristics that we mentioned before, to do that, the effect of the zero range potential is considered implementing a boundary condition in the wave function. Then for the many body problem, we consider the zero range effect putting this condition in the wave function. This means that if you have two particles with different spins, when the distance between this pair goes to 0, the wave function have to go like this, 1 over r minus 1 over a. Of course, for the unitary limit, this second term goes to 0, and the wave function have to go like 1 over r when a pair of particles with different spins are so close together. Okay, you can consider this boundary condition in the wave function, and at the same time, the Schrödinger equation reduces to this form, where we have just the kinetic term and the correct boundary condition in the wave function. And it's not necessary to put the potential term in the Hamiltonian. Okay, this boundary condition is called Wigner-Bett-Pires boundary condition. Okay. Now, how can we do that in a simulation, calculation, based in a quantum Monte Carlo strategy? Well, the methodology we employed is follow in principle the same strategy the original Monte Carlo, but with some differences to consider the Wigner-Bett-Pires condition, boundary condition. Okay, basically, we want to solve the Schrödinger equation for a system formed by n up particles and n down particles. We want to solve this problem, where R, this big R, is the configuration of the system. The first thing we have to do is to write some wave function model to describe the system. And this wave function must be antisymmetric. And in our case, we divide this wave function in two parts, basically. The first part is it's a product of pairs interaction that we call the Jastrow factor, the product of Jastrow factor, like this. And the second part is these two terms that basically contains the antisymmetric part of the wave function. Then this first phi is a determinant of Slater for the bath. I put n up particles in the bath, and we have a determinant for describe this part, to consider the antisymmetric part. And then another term is another determinant of Slater for the downspin particles. Of course, if you have just one particle, just one down particle, this last term reduces just for one term, and we don't have a determinant. Okay, another thing that we have to talk about this chose for the wave function is that the Jastrow factor is the responsible to give us the correct boundary condition in the wave function. In other words, we put the Wigner-Bett-Pires boundary condition inside this term. And the other terms are responsible to establish the node structure of the wave function. Okay. Now, in this way, writing with more details, the determinants of Slater can be writing like that, and we are putting plane waves to each term of the determinant. I mean, we can choose which momentum we want to put each particle in my system. We have to fill these momentum states from from 0 to the last moment states. Then with this form, where nx, ny, and nz are integer numbers that can vary from 0 to infinity, or minus infinity to plus infinity. And L is the size of the box of the simulation. Okay. Well, now we have to establish the main form, the functional form for the Jastrow factor. And this is maybe the most important part in the calculation, because for the zero-range model, we can put the Wigner boundary condition directly in this functional form. And one way to do that is choose a functional form for the gestural factor like this. Hyperbolic cosine over R. Then it's possible to show that this form has the correct boundary condition, just taking the limit where the distance between two particles with different spins goes to 0. And this form goes like 1 over R. Then this is possible to do that. And the another constants are considered to guarantee the continuity of the wave function. This lambda factor is chosen doing the first derivative of the wave function 0 in a range, and this n constant is a normalization factor for the gestural factor. Basically, we choose this n factor to do this term equals 1 in D for R equal T. This guarantees that the continuity of the wave function inside the box simulation. Okay. When you are considering the square wave potential, it's a little bit different. The square wave potential is this. Then in this case, it's different. We have in the Hamiltonian of the Schrödinger equation the kinetic term and the potential term. And the potential term is like that. You have a range, and for relative distances between the particles with different spins, the potential is minus V0. This V0 is the strength of the potential. And outside the well, for distances bigger than R0, the potential is 0. Then it's a very simple potential, but we can control in a easy way the value we choose for the range of the potential. Okay. To consider the gas interacting via the square wave potential at the unitary regime, you have to choose the value of the strength of the potential equals this expression. If you choose that, the scattering amplitude has the correct value that you have. The scattering length goes to infinity. Okay. Then the choice of the gestural factor in this model is different from the zero range option. We took another strategy to choose the gestural factor in this case. You do something like that. We solve the two-body Schrödinger equation in the square wave potential for the relative distances smaller than the range. In other words, inside the well, we solve the two-body Schrödinger equation and took the solution for the gestural factor. Outside the well, for distances bigger than the range and lower than the D, that's the range of the Hillen distance, we chose the same functional form that we used for the zero range model. In this case, it's possible to observe that for the case where R0 goes to 0, this solution is taken into account in a few regions of values for R, and this solution is considered like in the first option for the zero range. There is this similarity. But in this case, it's different because we are considering, in fact, the potential in the problem. Okay. Not just the kinetic term in the Hamiltonian. Okay. Also in this case, the parameters A, B, and lambda are considered to give the continuity of the wave function. For R equal R0, for the distance equal the R0, the range of the potential, and the value of the wave function for D, the Hillen distance. Okay. Well, now we have to do the the Monte Carlo simulation for both cases. Both cases, for the zero-range model and for the square well potential model. But the principle, the main idea about the methodology, the Monte Carlo, is the same. Basically, the simulation begins with the called variational Monte Carlo. In the variational Monte Carlo, the energy can be estimated like this expression. We just take the average value of the Hamiltonian in the system. I mean, you have to calculate this. Of course, we don't have the exact wave function of the system. Then we consider the trial wave function, like that functional form that I showed to you before, and we use that trial wave function to make this average value. Well, you can do that sampling a set of configurations distributed in accordance with the probability density obtained from this value, the density of probability calculated with psi t. We can do that implementing the Metropolis algorithm. Basically, we have some configuration of the system, and you try to move some particle in your system, and you can accept or reject this movement based in the Metropolis algorithm. And after repeat this process for many times, we have in the end a set of configurations distributed like this density of probability. And you can calculate the average of the property for these configurations. This is the first and the simplest way to calculate some expectation value of some operator in the computer, in the simulation. Basically, for the energy, we calculate the average value of the local energy like this for the set of configurations. Everything this works very good if you have a finite potential without problems, because you can calculate everything without the divergences. For the zero range, it's a little bit different, as I will show you in the next. Zero range model has divergences when the distance between the two particles with different spins goes to 0, because the wave functions goes like 1 over r. Then you have an infinity in this case. It's a trouble. You have to avoid that. This is the thing that you have to do. Then the strategy to avoid these problems is shown in this illustration. Once you have one configuration, in this picture I am showing the unpolarized gas, but it's the same idea for any cases, for one impurity or a different number of impurities. You have the up spins and the down spins particles, and you have some configuration, and you find the closest pair for this configuration sampled by the Metropolis algorithm. And finding these closest pair particles, you do another move for this closest pair. The move consists in exchange the position for this closest pair of particles. You change the position of these two particles. And you calculate the probability to the configuration with the interchange position of the particle, and consider in your calculations of the energy the two configurations, the original configuration and the interchanged configuration, putting the heat bath probability for the interchange calculated with this. And in this case, the local energy becomes this expression. We calculate the local energy for the new configuration, the interchanged, multiplied by the probability, and you sum this value with the local energy for the original configuration multiplied by the probability. Then this strategy removes the divergences in the variational calculation Monte Carlo. Okay. Now, we have to do more than just the variational calculation, because the variational calculation have another troubles, because once we calculate the expectation value with a tri-wave function model, the results are dependent on the results depends on this model. If the model is not so good, you can have some bias because of the model, and you can to improve that doing the called diffusion Monte Carlo calculation. And the main idea of the diffusion Monte Carlo calculation is like that: is you have to write the Schrödinger equation like a diffusion equation like that, where tau is the imaginary time and E0 is the ground state of the system. Then what you have to do is evolve the state of the system in imaginary time, and it's possible to show that when the imaginary time goes to infinity, you goes to exact ground state of the system. Yeah. Of course, you have in all the calculations with diffusion Monte Carlo, you have a bound state for the system because of the nodal structure of the wave function, and you have the exact value just if you have the exact nodal structure of the wave function. But you can obtain the exact value for the energy, for example, for that nodal structure of the wave function. Okay, the strategy to do that is write the propagation equation like this, and in this moment, the psi t is used like a guide function to guide the configurations, and you have to sample this term inside this integral. And we call this term propagator, and basically G is a Green's function defined in a small time, and this term defines how the system can be drifted in an imaginary time. I am in a R configuration, and I want to go to a R prime configuration, and this term defines how can I do that. Yeah. Okay. One of the ways to do that is to rewrite the propagator in terms of free particles propagator, like this. Then where this G0 is the propagator of free particles. When you write this, you can obtain an expression like this. Then basically what we have to do is to drift the particles like this G0, that is basically a free particles propagator with a drifted term like that. Then basically if I were in a air configuration, we can choose another configuration R prime, obtained sampling another configuration that obey this expression. And this exponential term is used to consider the wave of this configuration. Okay. Basically, there is another detail about this, because is that we can consider the configurations obtained in the variational Monte Carlo to do this drift process. Then we take the final configurations from the variational calculation to evolve these configurations in imaginary time, obeying these characteristics. Okay, once we evolve the system in imaginary time, the energy can be calculated through the mixed estimator like that. Everything this is good to use for the square well potential because you can calculate the local energy without many troubles and without divergences. Everything works better. Everything this works better than for the finite potential model. But again, for the zero-range model is a little bit different because you can have the same divergences we observe in the variational calculation. You have to avoid the divergences. In the diffusion Monte Carlo calculation, you can avoid these divergences doing another strategy to the drifted term. First thing we have to do is to write the propagator G like the propagator of two-body particles, this little g. Then you can write this propagator, and after this we can divide the propagator of the pairs, this g, in two contributions. We have then a contribution of the propagator of the relative distance between the particles and the propagator of the center of mass of the particles. Then we write this pair propagator like that, where this first term is the propagator for the relative distance, and the another term is a propagator for the center of mass. Then you have to propagate these two terms in the simulation. Basically, the way we are doing this diffusion of the particles is something like that. The center of mass of the propagator the center of mass propagate like free particles. Then we have some configuration of your system. You set all the pairs of the system, all the independent pairs of the system, and you propagate the first. You have to propagate the center of mass of these pairs, and after this, you can propagate you can use the two-body propagator to find or to sample another relative distance for the pair for the drifted configuration. And in our case, we construct this two-body propagator from the normalized solution of the scattered S-wave function. The result is used in some papers, but basically the solution for this propagator has two contributions. The first contribution is a free particle propagator for the relative distance, and the second term is the contribution of the S-wave scattering. Basically, you have to consider these two contributions to propagate the relative distance of the pairs. Well, everything this is not enough to remove the divergences in the calculations. And to remove the divergences, you have to consider in the calculation of the energy 4 different configurations. Basically, what we do, we have some pair, and we sample delta R to change the relative distance between the pair, and we consider a second configuration, R minus delta R, and the two more configurations with the exchanged position of the two first configurations. Then all these configurations, the 4 configurations, are considered in the calculations of the energy. Then we consider the probability of the 4 different configurations by this expression in equation 34. Okay, basically this strategy removes the divergences in calculations of the energy in diffusion Monte Carlo. Okay, Another thing you have to pay attention is about the calculation of the expectation value of some operator in our calculation. Assuming that the state of the system in some imaginary time tau is, can be written like this, then the expectation value for an operator that do not commute with the Hamiltonian is obtained through the extrapolator estimator. Then if you want to calculate the expectation value that do not commute with the Hamiltonian, we have to consider these. And in practice, what we have to do is calculate the expectation value of the operator in the variational level and in diffusion Monte Carlo level, and to make this consideration. If the operator is the Hamiltonian, it's possible to show that the extrapolated value is just the diffusion Monte Carlo energy that we have. Then, okay. Now, I will show you some results that we obtained using this methodology to the system we are interested. I mean, in the first figure, in the left side, we have the difference of energy of the system with just one impurity and the energy of the bath. Basically, we put the impurity in different values of the momentum of the impurity, and for 0 and the another values of the momentum, we choose that with that terms in the wave function, and x, and y, and z, and we calculate the difference of energy. It's interesting to observe that we have a linear behavior of this spectrum of energy as expected by us, because with the fitting of these points for the low momentum of the impurity, we can obtain the effective mass and we can obtain the binding energy just looking for the parameters of the line. Then it's a little bit simple. Okay, we can do that for the zero-range model that I am showing here, and you can do that for the square well model for different values of the range of the potential, and you do that for different values of the range for the square well potential. And in this right side, we show the results obtained for the square well potential. These green dots represents the value of the difference of the energy obtained for different values of the range of the square well potential. Then it's very interesting to note that first, the values goes to the zero-range model value that we obtained if you want to make some extrapolation. Then you can say that it's a characteristic of the universality behavior of the system. You can make some extrapolation and obtain the same energy. But it's important to note that the value obtained with the model depends on the range of the potential. Then if you are not considering a potential with a range small enough, you can obtain incorrect results for your properties. Okay, and now I am showing you the values of the polar non-properties that we obtain for the zero-range model and for the square well model as a function of the potential range. Basically, in the left side and in the right side, we put the parameters obtained with that line we showed in the last slide. You know, in this part is the effective mass, and the right side is the A parameter of the quasi-particle model we used to describe the polaron. Well, another thing we have to note is that our results has a very good agreement with another results. For example, the results obtained by Carlos Lobo and co-workers that I showed you in the beginning of my presentation represent like this. It's a little bit different, but this another results obtained 2 years after the first one by the same group. The first author is Pilati, 2018, has a better agreement with us. And you can observe a good agreement for the parameter A as well. And we have observed a good concordance with experimental results and diagrammatic results, or even variational results obtained with the Chevi ansatz. That maybe is one of the most famous variational model to simulate, to treat the polaron in these systems. Okay. And now, I am showing you the pair distribution function of unlike spins in the impurity Bath system, as a function of the distance. Basically, for the system with the Bath and just one impurity, I calculate the pair distribution function. And we can see the variational results, the blue results, the diffusion Monte Carlo results, and the extrapolated results, calculated by the two results, VNC and DNC results. We can make the extrapolated value of the property in both of cases. Then, in the inset of the figure, you show you the value of the pair distribution function multiplied by the squared distance. It's an important result because in this region where we can see a black line is the wave function is governed by the Wigner-Bethe-Pires condition. Basically, this shows us that the wave function obeys that behavior I showed you before. The wave function goes like 1 over r. Okay. But as a consequence, the pair distribution function goes like that. Okay. Besides that, we can obtain another important property from that result I showed you, because the tail of the momentum distribution can be associated with a parameter c when the momentum goes to infinity. Basically, this parameter c is a measure of the short-range correlations among atoms in different spin states for a given concentration. We call this parameter the contact parameter. You know, it's the contact parameter. This is associated with the momentum distribution like that. And in practice, in our simulation, you can obtain this property with the results we obtain to G of R. Because basically there is a direct relation between G of R and the momentum distribution. Okay, to do that, we have to observe the behavior of G of R when the distance of the particle goes to 0. And we can see that the behavior of G of R has a structure like that. Then you can make a fit of the results and to obtain the contact parameter. Okay, but in the practice, we can rewrite this expression 38 to write the pair distribution function as a function of this difference C, that is a dimensionless contact per unit volume. You can compare this dimensionless property with the experimental in a easiest way. Basically, the relation between this first contact parameter and this another one is an expression like this. Okay. This is the contact parameter per unit of volume as a function of the potential range for one downspin impurity in a bath with n up particles. So, I mean, we put one impurity in a bath and calculate the GOR, make a fit, and obtain the contact parameter. And you do that as a function of the range of the potential, and this black squared is the result for the zero-range model. This region with a shadow is basically the dispersion of the square wave results, the dispersion, and the fitted line is a fit with the square wave results. Basically, it's this. Okay. And the inset, we show the results of the contact obtained to the unpolarized gas. And we can put the same number of the impurities and the same number of the particles in the bath, and you can calculate the contact as well. Of course, the value is very different, Okay, and now I would like to show you the results obtained for the system with different concentrations of impurities. Basically, we put the bath and we increase the number of the impurities, varying the n down, the x value. We use two different number of particles for the bath, 33 and 57 particles in the bath. We can see these red dots. It's the different the results obtained for the different number of particles in the bath. And it's important to show that if you increase the number of the particles in the bath, the behavior of the energy is the same. The points follow the same trend in the same curve, and it's important to note that. Another thing you have to note is that the blue dots are the results obtained for the fillet shells case. I mean, we fill the system with the impurities until have a fillet momentum level, and it's indifferent. The results doesn't change as well. We can put a fillet or not fillet shell that is the same result, the same behavior. Okay. When you increase the value of the range of the potential, the results are affected. Basically, the energy increase like that. We have the zero range, the squares, the solid squares, and after this we have the range of the square wave potential equals 0.03. It's almost the same results of the zero range, and increasing the value of the range of the square wave potential, we increase the energy like we can observe in the figure. Okay, and the lines are the fit for the Landau-Pomeranchuk model that I showed you in the beginning of the presentation. The model is a good description for the system with the concentration of impurity is not so big. Basically, the literature suggests more 2010 that the model is good until the concentration equals 0.5. Then basically we fit that model until the concentration equals 0.5. We use the values of the effective mass and the A parameter, and basically we have to fit just that F term in the model that I showed you. The F term that takes account about the interaction between two polarons. This dashed black line is the zero-range equation doing the F parameter equals 0. Then we can show the importance of the interaction of polarons in your system. You know, if you don't have the interaction in your model, you have this dashed line, and putting the interaction between the polarons, you have the another options. Okay, now I'll show you the values obtaining for the F parameter. You can see a lot of points, then I will explain you all of this. I think that's many information in this figure, but basically you have this square solid point, black point, for the zero range model, the parameter obtained with the fit of the Landau-Pomeranian-Schuck model, and we have the black dots, the solid one, either the results for the square well potential as a function of the range of potential. Also, in this case, we can see a good extrapolation for the range of the potential 0. Then you can see that universal behavior for this case as well. And you can see a good agreement with the values in the literature. For example, Pilati, 2008, and for analytical results obtained by Mora and Chevy, 2010, this the red triangle. We can see another analytical results for F. It's an analytical results obtained that obtains F as a function of just the parameter A. Then we have a good agreement, and in the end we can observe a good concordance, a good agreement with these results and the results obtained considering just the difference, the energies of the systems. I mean, we can put the system with the bath and two impurities, calculate the energy, and you can subtract from this energy the energy of the systems containing just one impurity and the another impurity. And with this way, you can obtain these empty symbols represented in the figure. Okay. Wow. Now, in the end, I have some conclusions about the work. Basically, the Wigner-Bethe-Pires boundary condition is considered in the calculation where then we have a model of, or a way to make a quantum simulation of the system without any extrapolation of the potential. We can do that and obtain results that don't depend on the range of the potential. We can do the properties directly without any extrapolation. Another conclusion, the results for the zero-range model are free from any bias arising from the extrapolation of the potential, as I mentioned before. Then it's very good because most of the calculations, most of the quantum Monte Carlo calculations use that strategy to do some extrapolation in some moment. And as we saw in my presentation, if you don't take care about the value of the range, you can get wrong results for the properties you are calculating. Okay, another important thing, estimations of properties such as polaron binding energy effective mass, contact, and the role of different concentrations were found to depend on the range of the potential. All the properties we calculate depends on the range of the potential. And of course, you can see a good extrapolation for the range equals 0, but with the another methodology for the zero-range model, it's not necessary this extrapolation. Okay, we have observed that using an effective potential with finite range can impact the estimation of ground state proportions of Fermi polarons. I mean, that if you want to simulate a gas in zero-range model, we have to, I think that it's a better option to use the zero-range model strategy to calculate the properties. In the same idea can be employed to different values of scattering lengths. You can use the same strategy. The main thing that you have to change is the boundary condition of the wave function. You can do that. We do that for unpolarized Fermi gases, and the results are very good, but we don't have these results yet for the polaron case for different values of scattering length. Okay. We have some perspectives about this polaron problem. Maybe the first problem we are interested is consider ionic polaron. Recent papers consider this problem for a Bose-Einstein condensate. Basically, they calculate these properties of the polarons for a system of bosons, boson particles. The strategy is similar than we have here. They used quantum Monte Carlo simulations to calculate the properties, but putting an ionic particle like an impurity in the bath. And it's a very, very interesting problem. And another recent theoretical result. This was, sorry about that. In this case, I think that the reference of this paper was not shown properly, but it's a paper from the last year, 2021. Okay, but this another one is a paper of ionic impurity in a bath of Fermi particles. It's similar that we are doing, but here they use another strategy to calculate the properties of the polaron based in theoretical strategy. And there is no results with quantum Monte Carlo of these ionic polarons for Fermi gases in this moment. And it's a very, very interesting thing that we have to do maybe this year or I don't know. Of course, besides that, we are interested to observe the behavior of the properties that we calculated as a function of the scatter length, not just in the unitary limit. This is a very, very interesting problem as well. Okay. Okay, thank you for listening. Thank the Brazilian agents, my collaborators. Thank you. I think they are in this moment watching on the internet. Thank you. And if you have some question, I am here. And I'm glad to give some answer. Thank you.
Okay, thank you very much, Renato. So, unfortunately, due to time problems, we are not able to take questions here.
Okay.
But if you have any questions, please write in email. We can provide it at the end of the talk. And thank you very much. Let us thank the speaker again.
Thank you.
Okay, so now let us welcome Diego Paiva Pires. He is graduated in physics in the Federal University of São Carlos, and he obtained his master and PhD titles here at São Carlos Institute of Physics. He is currently a professor at the Federal University of Maranhão, and his current research interest includes geometry of quantum information, quantum metrology, quantum speed limits, quantum coherence, characterization, and the quantum dynamics of closed and open systems.
Can you hear me? So, thank you for the gentle introduction. First of all, I would like to thank the organizers for giving me the opportunity to talk in this nice school. And in this talk, I will try to answer this question that it's posed here. How fast can a quantum state evolve under a given dynamics? And I hope to show you, I hope to convince you that this is an interesting question. And the answer of this problem is quite related to a concept called quantum speed limit. And I hope to convince you that this is an interesting problem. And the solution of this problem applies, finds applications in a range of problems that involves quantum thermodynamics, quantum metrology, dynamics of few body systems, or even many particle systems. So let us first discuss some motivations. And the point is, suppose you have a given quantum state, and here I will mainly focus on systems which has a finite dimension. And suppose you prepare a quantum system in an initial state that is given here, psi naught. And then you apply some evolution on this state. And after some time, let's say tau, the system reaches this final state. Well, given this evolution, given this, let's say this quantum channel, this physical process that in principle is arbitrary. The question is how fast the system evolves from this initial state to this final state. Or is there, the question can be posed in this way: is there some lower bound on the time of evolution between these two states? And of course, the idea here is discuss this problem in the context of some constraint. So suppose you ask that the initial state and the final state, these two states should be orthogonal each other. What is this minimal time of evolution such that the final state is maximally distinguishable related to the initial state? Well, here I have this cartoon. You can see this evolution depicted here. The system is initially described by this state psi naught, and then in some intermediate part of this evolution, you have this instantaneous state, this psi of t, and then the system reaches this final state. Essentially, when you have a quantum system and the initial state is a pure state, you measure this state with some certain probability. this state is a pure state. And then you can see the evolution of the system as some rays. Technically, the system describes some evolution in a space called projective space. But this is just a technical detail. So our point here is discuss how fast can this state evolve under some given dynamics. I mean, this evolution can be in principle a unitary evolution. I mean, you may have some closed quantum system, or this evolution can be modeled as a Lindblad master equation, for example, and then you describe an open quantum system. I mean, you have a system, for example, in contact with some environment, and then there is some flow of information from the system to this environment. So that, in principle, this happens every day, every time. I mean, you have some loss of information from the system to the environment. That is how nature, in principle, works. So the question is, quantum mechanics imposes a lower bound or an upper bound on the time of evolution. And to answer this question, I hope to show you that the distinguishability of these states plays a crucial role. I mean, to answer what is this time of evolution, what is this minimum time of evolution, such that the final and initial state are orthogonal each other, we need to know how to distinguish these two states. I mean, we need some framework in order to know how these two states are distinguishable. And then this problem essentially describes the so-called quantum speed limit. I mean, the minimum time of evolution between two given states. And then to give an idea of this problem in the literature, I will somehow back to the origins and discuss the main results of this involving this concept. And to do that, let us imagine a closed quantum system. And again, here I'm just considering finite dimensional. I'm just considering quantum systems that presents finite dimension. And then suppose you have this closed quantum system. I mean, the evolution is essentially unitary. The dynamics of the system is governed by the Hamiltonian. In principle, here we can consider for simplicity a time-independent Hamiltonian. And then the evolution is dictated by this unitary operator, essentially the time evolution operator. And then if the system is initially described by this C naught, you evolve the system and then reaches an instantaneous state of the system. And the point is, can we say something about this time of evolution between these two states? I mean, suppose you evolve the system under this unitary dynamics, and then you want to know something about this time tau. I mean, how can we, is there something that we can say about this time tau? I mean, what about the minimum time of evolution between these two states? I mean, I hope you are understanding this point. I mean, I hope to show you that quantum mechanics imposes some threshold on the time of evolution. So geometrically, we have this kind of depiction here. I mean, we can imagine each state of the quantum system as a point in a manifold. So here I have this surface M, and then the system is initialized at an state C naught here. This system evolves unitarily, and then at some time t, the system reaches this state. And of course, you may find some neighbor state of this psi of t. Let us call this state as psi of t plus dt. I mean, it's just this state psi of tau is slightly changing. It's just the state psi of t with a slightly change this time with this infinitesimal quantity dt. And then the system finally reaches this state. For each point here, you can depict this, let's say, this tangent space. I mean, if you know, if you want to understand, if you want to understand something about the dynamics of the system, you can take this tangent space. I mean, essentially you take some derivative of this state C of t regarding t, and then you will obtain nothing but the von Neumann equation for this state, since the dynamics is governed by the Hamiltonian H, which is in principle time independent. So to understand this quantum speed limit problem, we need to discuss this remarkable result from Understand and Thumb. These two guys, they have shown that if we initialize the quantum system, the closed quantum system, at a state C naught, and evolve this system unitarily with some time-independent Hamiltonian, and then you reach this final state C of tau, these guys have shown that the time of evolution, this time tau, is lower bounded by this quantity. So here, what we have here, we have this time of evolution tau, and in the left side of this inequality, and in the right side of this inequality, we have this delta H, which is not nothing but the variance of the Hamiltonian that governs this the dynamics, the unitary dynamics of the system. Essentially, this is, if you want, this is the standard the variance, the square root of the variance, and here we have this arc cosine of this quantity. I mean, we have inside here this kind of overlap. I mean, you take the projection of the initial state and the final state evaluated at this time tau. Well, we need to understand this quantity, but note that this time of evolution is given by an inequality and not but an equality. That is a remarkable result. This means that somehow time and energy should satisfy some inequality that resembles the Heisenberg uncertainty relation. But the point is, in quantum mechanics, we know that there is no an observable that describes the time. I mean, there's no such Hermitian operator that could describe the time as the time that we measure in some clock, for example. As well, the energy is described by the Hamiltonian. So the main point here is this time of evolution is inversely proportional of the variance of the Hamiltonian of the system evaluated at the initial state of this quantum system. And here we have this function that somehow measures the distinguishability between these two states. I mean, this result is general. I mean, you have a closed quantum system, a time-independent Hamiltonian, an initial state C naught, and a final state C tau. Here, we do not impose any constraint between these two states. But interesting, if we impose that these two states should be orthogonal each other, I mean, this overlap should be equal to 0. I mean, these two states, when these two states are orthogonal each other, they are maximal distinguishable states. Then this overlap should be equal to 0, and this arc cosine is equal to pi over 2. And then this inequality collapses in this simplest inequality. I mean, here, this inequality here is more complicated because the right hand side of the inequality depends on time. Essentially, we need to solve this inequality applying some technique, for example, numerically. But if we impose this constraint that the system, the closed quantum system, evolved between two orthogonal states, we find this more simplest inequality. And this is nice because this means that the time of evolution, let's say the total time of evolution, satisfies some lower bound. I mean, there is some kind of threshold. And the minimum value of this time tau is given by this quantity here. I mean, this quantum speed limit time, this QSL for orthogonal states. Somehow this product delta H, this variance times the tau, defines an intrinsic time scale of the unitary quantum dynamics of the system. Here, we should point out that there's no time-energy uncertainty relation, just because time is not described by a Hermitian operator in quantum mechanics. Of course, there's some special case in which you can build up some operator with some particular properties that somehow fulfill an inequality that gives you a time uncertainty relation. But this is not general. In general, there's no such Hermitian operator for time in quantum mechanics, although we have energy described as eigenvalues of the Hamiltonian. So this is nice. Well, this inequality essentially answered part of our problem. I mean, if you increase the variance, you should decrease the right hand side of this inequality. So in order to answer how fast can the system evolve under two states, if you impose some orthogonality constraint between the two states, you can understand how fast the system evolves by playing with the variance of the Hamiltonian. And then you just look for the Hamiltonian that decrease or increase the right-hand side of this inequality. But look, this result comes from the 50s, let's say. The point is, well, let us understand this situation here with a concrete example. Let us consider a single qubit. I mean, we just have a two-level system. So the Hamiltonian of the system is given by this quantity here. H bar omega essentially gives you some the energies, and this omega is nothing but the gap between the two levels of the system. So suppose you initialize your quantum system at this state. You have this kind of superposition of these two states, 0 and 1. And these two states, they describe the building blocks of the computational basis. So if since the system is closed, you have a closed quantum system, you evolve this initial state unitarily. I mean, you evaluate from this Hamiltonian the time evolution operator, and then is a simple task to obtain this state. And of course, this state is evaluated at a time tau. And if you take the overlap between the initial and the final state, evaluate the variance of the Hamiltonian, you should obtain this inequality. I mean, this is the inequality from Mandelstam and Tan. And playing with this inequality, you just arrive at this result here. So you need to evaluate this overlap and take the square, the absolute value, and then the square, which is here, which is given here. And then you evaluate the right-hand side and obtain this cosine, the squared cosine of the variance time over h bar. So this is this is quite difficult to understand. And then I illustrate this with this plot. So in this plot, we have the following. The blue line represents the right-hand side of the inequality. The red dashed line describes the left-hand side. So you see that if we change this product frequency and times tau, frequency times the time of the problem, we see that the inequality is saturated in this region. What this means? When I say that the inequality is saturated, I mean that this inequality turns to an equality. I mean, for this region, for this let's say for this omega t in this region, this inequality is nothing but an equality. So I should say that in this region, the evolution of the system follows, let's say, the geodesic that connect the initial and the final state. The point here is that you can understand the evolution of the system geometrically, and I will show this in the next slides. But here we have, let's say, the first indication that you can see the problem in this way. So in this region, the inequality turns to be an equality. But you see that in this region of omega times tau, well, we have an inequality, because you see that the left hand side of inequality is quite different of the right hand side. Of course, these functions are periodic, and you see the same thing for larger values of this omega times tau. But the point is, there is some range of these parameters omega tau in which this inequality is nothing but an equality. And this gray region here means that the system cannot reach the dynamics of the system cannot reach this region. I mean, this is a forbidden region if you think about the dynamics. And you might conclude this just look into the functions. I mean, you see that the blue line here plays a role of a lower bound of this left-hand side. So this is just an example. I mean, this is a quite simple example, because here we have a two-level system. Of course, you might apply this result for systems with many particle systems, more complicated as you want, and of course for more complicated Hamiltonians and for more complicated initial states. Well, almost 50 years after the result from Modest and Tan, these two guys, Margolus and Levintan, have addressed the same problem, but look into a different perspective. Well, Margolus and Modest and Tan have considered the variance of the Hamiltonian. I mean, this minimum time of evolution depends crucially of the variance of the Hamiltonian, the generator of the unitary dynamics. But these two guys have shown that if you have some initial state, I mean, if you have a Hamiltonian, if you know the energies of the Hamiltonian, if you know the spectrum of the Hamiltonian, you can write down any initial state of the system as a linear combination of the eigenstates of this Hamiltonian. And then after some math, you can show that this time of evolution between an initial state and a final state, and imposing a constraint that these two states should be orthogonal to each other, this time of evolution depends not on the variance of the Hamiltonian, but on the mean, let's say, the mean value of the Hamiltonian regarding to the initial state. Here, for simplicity, we consider, well, these guys have considered the ground state of the Hamiltonian having zero energy. Well, we have a finite dimensional system. You have, let's say, a number n of levels, and the ground state is chosen to be of energy zero. You can, well, you can consider this just a simplification, since you can choose this energy having any value and just introducing some, let's say, some shifting on the spectrum. So, but the point here is, if the initial state and the final state are orthogonal to each other, if they are maximally distinguishable states, this time of evolution depends on this mean value of the Hamiltonian. So you see that we have two results describing the same problem. Well, this situation is quite different, because let's say, if you know the Hamiltonian and the initial state, you can check this result and then compare with the result from Modest and Tan. And we can see here that this time, this QSL time, this lower bound of the time of evolution, on the one hand is described by 1 over the mean value of the Hamiltonian, and in the other hand is described essentially by the inverse of the variance. But well, how nature works? Well, I think that nature does not choose one value instead of other. And then what is the point here? I mean, how can we, let's say, unify these two results? How can we find some way to explain why these two results are different each other? And how can we in some way find the general result that gives the precise answer of this problem. So what is the minimum time of evolution for a given quantum state, a given quantum system evolving unitarily from two maximally distinguishable states. And then after the work by Margulis Levintan, Levintan and Toffoli have presented the answer for this problem. I mean, this minimum time of evolution is given not but not in favor one result in detriment of the other. I mean, the minimum time of evolution is given by by taking the maximum value between the two results. I mean, here we have the result from Mandelstam, and here we have the result from Margulis-Levitin. And then this minimum time of evolution is given is obtained by taking the maximum value between these two results. So this minimum time essentially sets the fastest attainable time scale over which a given quantum system can evolve. Of course, here we have an initial pure state and a final pure state. This result does not take into account mixed states, for example. And this result just answer part of our problem, because we are answering the problem regarding this time of evolution for closed quantum systems. Of course, we have open quantum systems. So after these results, a lot of papers have appeared in the literature. Here I have a collection of them, and part of these results have tried to generalize the previous results when considering initial mixed states, not just initial pure states. And most importantly, these results have tried to address the problem of the dynamics of open quantum systems. So here we have these three papers here. Let's say one of the most important papers covering this subject in the literature. And this paper this paper have discussed essentially this quantum speed limit for physical process, but considering a particular way to distinguish the two states. If you remember, the result from Mandelstam depends on some overlap between the initial and the final state. If you keep track on this result, you should conclude that this overlap plays a role of some fidelity. I think most of you have heard about this word, this quantum fidelity, and this is the function. This is let's say the figure of merit, the information theoretic quantifier that have been used to distinguish two quantum states. And of course, these two papers here have considered the same approach, but they have shown some different. They have presented some different perspectives. This paper here, in this paper here, the authors have shown that entanglement play a role on this time of evolution. I mean, if you have an initial state which exhibits some correlations, this evolution should be faster. And in this paper, the authors have considered that have considered an open quantum system that exhibits some non-Markovian signatures. I mean, the dynamics shows some memory. The master equation, I mean, there's some technique, I will skip these details, but the point is they have shown that this non-Markovian signature also promotes some speed up on the evolution of the system. But the point is, now we understand this is not the case. This result just apply to some particular initial state. This is not a general result. So a lot of results have appeared. Here I have my sense to this problem. And in this paper, which mostly is the paper concerning this talk, we have presented some geometric framework to analyze this problem. And in these two papers, I have discussed some applications of this geometric feature. And then in the rest of the talk, I hope to explain the details about this work, and then at the end show you some interesting applications. So my goal here is try to answer these questions. I mean, is it possible to generalize these previous results that these people addressed in the literature? Is there some let's say some general way to formulate this problem? I mean, can we formulate this quantum speed limit problem for both unitary and non-unitary evolutions? I mean, can we say something about this minimum time of evolution for both closed quantum systems and open quantum systems? And doing this, and by doing this, we should use, or we should apply some general theoretical formulation. What about some general physical process? I mean, suppose you have a given quantum system, a multi-particle system, an initial state that exhibits some correlations, multipartite state. How can we say something about the evolution, the time of evolution of the system? I mean, answering these questions, we also contribute to understand how fast can we process information. So this problem is important. And what happens when we consider initial and final states that are orthogonal or non-orthogonal? I mean, what happens when you have maximally distinguishable states, and when you have two states that you cannot say so much about the distinguishability? And what happens when the initial state is pure, and of course the final state is pure, a pure state? And what happens when the initial state of the system is a mixed state? I mean, you have a statistical mixture of some pure states. I mean, you measure the system, and for each measure, you have some probability to obtain some pure state. And of course, can we say something about this time of evolution going beyond this formalism of this quantum fidelities? I mean, again, if you remember the result from Manders and Tam, the time of evolution, the minimum time of evolution, depend on some overlap. That overlap is somehow related to the fidelity between the initial and final state. And this quantity is also related to this quantum Fisher information. This is a very important quantity in information science. And today, a lot of papers discuss this quantum information to study some properties of quantum systems. So to generalize the problem, we consider the following. Suppose, again, you have an initial state, you evolve this state by some evolution. I mean, this evolution here can be an open, this evolution can be a unitary evolution or a non-unitary evolution. I mean, you may have a closed quantum system or an open quantum system, and after some time, the system reaches this final state. The point here is the initial state is not a pure state. I mean, it could be a mixed state, and of course, the final state can also be a mixed state. So geometrically, we have the following. Each state of the system can be seen, might be seen as a point in some surface. Let's say this manifold of states. So the system is initialized here, and then you apply this evolution. This evolution could be anything. Well, again, unitary evolution or non-unitary evolution. The system the evolution of the system geometrically will follow a path. I mean, you can keep track on the evolution, and you essentially see a path being drawn here in this surface. So, of course, you can imagine a lot of paths. I mean, for a given dynamics, for a given time t, the system may follow some path. This path will connect the initial state and the final state. So, of course, you can imagine an infinite number of paths that connect the initial and the final states of the system. But among those paths, you will find some particular path that exhibits the shortest length between the initial and the final state. I mean, for each path here, let's say for this blue path, you can measure the distance between the initial state and the final state. I mean, for each path related to the evolution of the system between these two states, you can calculate this distance. But the point is, among this infinity number of paths, you may find a particular path, let's say the geodesic path that connects the initial and the final state. And this path presents the shortest length, the shortest distance between these two states. Well, here we have nothing but the least action principle, similar with what happens in classical mechanics. And I will show how this works in the next slides. Well, thinking in this way, we can propose this inequality. I mean, suppose that the geodesic path have some length that is given by this function here, this capital L that depends on the initial and the final state, and this length is less than the length of any path that connects the initial and the final state of the system. So we have this important, essentially, we have this crucial inequality that will give us some route to discuss this generalization of the quantum speed limit problem. Well, again, we have the length of the geodesic connecting initial and final states, and the length of any path that connect initial and final state. So our puzzle is to discuss this minimum time of evolution. I will show you that to discuss this problem, we can essentially solve this inequality. But to solve this inequality, we need to understand, well, how can we calculate, how can we evaluate this function capital L? Well, the length of the shortest path, this geodesic connecting initial and final states. And how can we understand this length, this function here? I mean, for each path connecting initial and final state, we can label this path with some length. And how can we calculate this length? Well, here I have some technical details. I will not go into the detail, let's say the details of it, but just to give you an idea, here we consider initial mixed states, and by hypothesis we know the spectral decomposition of this initial state. I mean, we know the eigenvalues, these probabilities of measuring the system, the initial state of the system, and we know the eigenstates of this system. This row of T here describes the density matrix of the system. Essentially here we have a statistical mixture. Well, every time you measure some eigenstate J, you have some probability P of J. And in principle, since the evolution is arbitrary, these probabilities might depend on time, and these eigenstates might depend on time. So we have this important theorem that gives the first answer to our problem. I mean, if you think about the evolution of the system along a single path, I mean, you have the initial state, you apply the dynamics, the system evolves following this path, and then after some time t, you have this instantaneous state rho of t. There is some neighbor state, this state rho t plus d rho of t. I mean, essentially, we have some perturbation of this state rho of t for and then we get this neighbor state, and well, following this path, we finally reach this state rho of tau. To to answer the question of how evaluating the length of this path, we first answer the question, how can we evaluate the distance between two neighbor states? I mean, if you take some state rho of t, and this neighbor state rho of t plus d rho of t, how can we distinguish these two states? I mean, what about the distance between these two states? Well, there is some important theorem, this Morozova-Chenkov-Petz theorem, that gives the answer of this problem, to this problem. I mean, the distance between two neighbor states is given by this function. I mean, this is a bit complicated function, but I will try to explain the meaning of each contribution. Well, this function, this ds2 squared, essentially describes a line element. Okay, this is an infinitesimal distance between these two neighbor states, and this distance depends on this contribution. And this contribution is related to this Fisher information I will show you in the next slides. And this contribution here is important because it is related to the quantumness of the problem. I mean, if you have an initial state which has not coherences, this contribution is always there. I mean, this contribution is related to, let's say, classical probabilities. An initial state that is fully diagonal. But if this is the initial state of the system, the density matrix of the system exhibits some non-zero coherences, I mean, non-zero elements out of the diagonal of this density matrix, you should have this contribution here. This contribution comes from the, let's say, the quantumness of the state. And why? Well, we have this quantity here, the absolute value of this d rho JL. This is nothing but the coherences of the, let's say, the change of the state rho regarding this basis, this basis of states J of L. And if you remember, these states J and L, they are eigenstates of the initial state of the system. So here we have this function C, and this function C satisfies some properties. I will not go into the details, but the point is here I have some plot. I mean, this function C depends on another function which I will call f, and here I plot this function f. You can have any function f if these functions that you choose fits inside this blue region here. I mean, you can check that there is always some minimum value for this function and a maximum value for this function, and you can choose any function f since this function fits inside this blue region. And of course, since you are imposing some constraint to this function f, you impose some constraint to this function c. And well, how can I see that by using this function here, I can distinguish these two states and obtain this quantum Fisher information and another information theoretic quantifier? Well, each function f is related to some information theoretic quantifier. In particular, if you choose this function described by this red line here, you have the so-called quantum Fisher information, which is related to the fidelity. And this fidelity appears in the result of time of evolution obtained by Mandel-Stanton. But if you use this function f w epsilon here, this blue dotted function here, you have a different information quantifier, theoretic quantifier called Wigner-Renas skew information. So what is important here? This function gives the, let's say, the infinitesimal distance between these two states here. If I take this integral along all the path connecting the initial and the final states, I will obtain the length of this path. So this is a crucial ingredient to address this problem of quantum speed limits using this geometric approach. Well, okay, we have some receipt to evaluate the right-hand side of this inequality. But how can we evaluate the left-hand side of this inequality? Well, if we are able to evaluate this quantity here, we can extremize this functional for each dynamics for a given initial state, and we will obtain this function here. And if you remember, this function is nothing but the geodesic, the length of the shortest path connecting the initial and the final state. Of course, this is a formidable problem, computational problem. This is quite complicated. And it can be done, at least numerically, but analytically, we just have a few answers for this function. I mean, for each function C, I will have some function L, some distance between the initial and the final state for a given path. If you extremize this function, if you minimize this function, you will have the geodesic length related to this chosen function C. So just to understand, we have some function f, let's say some input function. We evaluate this function C, and then we calculate this line element. We integrate this line element along all the path connecting, along the whole path connecting the initial and the final states. And then we have this functional. Of course, this functional is a function of the initial and final states. If you are able to minimize this functional, you have the left-hand side of this inequality. I mean, this geodesic length, the length of the shortest path. Well, since we are discussing the time, we can prove that this line element can be written in this way. I mean, we have two contributions here. The first one is related to the so-called quantum Fisher information, and the second one is related to the coherences of the changed state in time, this infinitesimal variation of the initial state. So here we have this quantum Fisher information, and as I told you before, this quantity is always there. I mean, if you have a system described initially by any state that is nothing but a classical state, I mean, a fully diagonal state, you always have this contribution, this Fisher information. But this quantity comes from this quantumness, and we can prove that these quantities here, this A, J of L, are somehow related to this quantity called connection. I mean, if you study geometric phases, you just realize that this quantity here is nothing but the connection regarding to geometric phases. So if you are able to calculate these two quantities, you are able to calculate this function L, I mean the length of the path connecting initial and final states. You extremize, you minimize this functional, and you have the left-hand side of the inequality. But this is a difficult task, and we may use some analytical results for this function. I mean, the mathematicians have proven that for some functions f, we have analytical expressions for this function capital L. And we have at least analytical expressions for this function L for two of these functions. In particular for this maximum function, this f, that is related to this Fisher information, and for this function f here, that is related to the Wigner-Renas skew information. So if you have the left-hand side and the right-hand side, you solve this inequality, and then you will get the time of evolution between the initial and final state without imposing any constraint between these two states. I mean, here, what I have an initial state, a final state, a given dynamics, which could be unitary or non-unitary, and then I ask myself about this time t, time tau, between the evolution of these states. Okay? Well, solving this inequality could be quite complicated. And why? Well, we have a lot of possible initial states. An initial rho Renato that is related to a field-body quantum system, or an initial state rho Renato that is that is given by a multiparticle state. An initial state that could exhibit correlations or not. And we have some dynamics, and these dynamics could be very complicated. So instead of solving this inequality, we can propose a quantity that I will call a figure of merit. I mean, I will introduce this function, and if you see here what we have the right-hand side of the inequality minus the left-hand side of the inequality. What this means, if you remember, when I presented the example of this speed limit for the two-level system, I have showed you some region in which the inequality turns to be an equality. And for some dynamics, for some initial state, I should observe the same here. Of course, this not happens for any initial state or any dynamics, but this happens for some initial state and for some dynamics. Okay, and every time this inequality turns to be an equality, we will conclude that this function delta goes to 0. So every time the system follows the geodesic path connecting the initial and final states, we saturate this inequality, and this figure of merit goes to 0. So we just change the way to look to this problem. Instead of searching for this time tau, I will just search for the zeros of this function, delta, for some initial state, for some dynamics. But if you see, this problem is more complicated than that, because we have some figure of merit that depends on the initial state, the dynamics, and this function f. I mean, we can choose any function f that satisfies the constraint. I mean, any function that fits inside this blue region here. Any function f has a clear meaning in the perspective of information science. And as I told you, this function here, this linear function, is related to this Fisher information. And this blue dotted line, this Wigner-Anasas information. So we have at least, let's say, three parameters, if you want to think in this way. We have this function, we have the initial state of the system, and we have the kind of the dynamics. I mean, a Hamiltonian, a Lindblad superoperator, or a family of Krauss operator if you think about a quantum chain. So to find the zeros of this function, we should maximize, we should extremize essentially this function over all the possible functions f that fits inside this region. Of course, again, this is quite complicated. And to understand this problem in a properly way, and of course to conclude my talk, I will present you some examples in which we observe the saturation of this inequality. I mean, we find this minimum time of evolution just looking to the zeros of this function. So let us consider the unitary evolution, and I will show you the power of our approach. I mean, I will obtain in the next slides the same results that Manders and Tan have obtained in the past. And of course, by using this framework, we can obtain some other results obtained, discussed in the literature in the past years. So in particular, if you choose this function C of f in this way, I mean, if you choose this function here, this linear function, and you play the math, you just find this inequality. I mean, the time of evolution is given in this way. And here, what we have the inverse of the variance of the system. So since we have the unitary evolution, we have a closed quantum system, that the dynamics is generated by a Hamiltonian. And this Hamiltonian can be, in principle, time dependent. And because of that, instead of having just the variance of the Hamiltonian, we have this the time average of the variance of the Hamiltonian. So this result somehow generalized the result obtained by Mandelstam and the results discussed in these two references given here. And here, what we have here, we have this function L. This function L is nothing but the so-called Pires angle. Well, this depends on this arc cosine of this function. This function here is the quantum fidelity. When I have an initial state rho naught and a final state rho of tau that are in principle mixed states. You can prove that if this state rho naught is a pure state, and of course this rho of tau is also a pure state, this result here should collapse into the result from obtained by Mandelstam. I mean, this is just a complicated function to describe the overlap between the initial and the final state when both of these states are mixed states. Okay? Well, this is nice because we are showing that our results somehow generalizes previous results for the unitary evolution. And of course, if we choose another function C, for example, this function, which is related to this information theoretic quantifier called Wigner-Renato information, we obtain this inequality. Well, the time of evolution is lower bounded by this function. Well, the right-hand side of this inequality is inversely proportional to this time average. I mean, the time average of this quantity. This quantity here, it's not so complicated, and the physical meaning is the following. Well, first of all, it is called Wigner-Renato information, the quantity inside the square root, and somehow gives you some information about the coherences of the state rho of t in this case, and regarding the Hamiltonian of the system. I mean, when the Hamiltonian commutes with the square root of the state of the system, the evolved state of the system, this quantity should be 0. Okay? And then we have this function L, which is given by the arc cosine of this quantity here. If you see, these two quantities are quite similar, and there is some reason for that. This quantity here is a particular case of this one. I mean, this is the quantum fidelity, and this is called the quantum affinity. I mean, you show that this quantity, this quantity is recovered by this quantity when these two states commute each other. Okay. So, and finally, well, I will skip this detail. And the main message in this slide is that we have shown that for any initial state, in this case, we have, of course, a two-level system, and then we parameterize the state of the system in the Bloch sphere, and then we have this initial state, and we evolve this initial state with any unitary evolution. Of course, there's some technical details, I will skip them. And what we find is that this figure of merit approaches 0 for some chosen parameters. I mean, when you choose this parameter phi, you can see that there are some regions for which this quantity, this figure of merit approaches 0. And this should hold for any initial state. And well, although I will show in here the result for the two-level system, we can generalize for any system which has finite dimension. I mean, we can have not just a qubit, but a qubit. Okay, and to conclude, I will present this result regarding the open quantum system. I mean, I have this amplitude damping, and the picture is the following. Imagine that you have a two-level system, and the initial state of the system is given by this density matrix here. Of course, I am parameterizing the initial state on the Bloch sphere, and then the initial state of a two-level system is given by this sphere in blue, okay? This system is in contact, this two-level system is in contact with some environment, and then the system changes some information with this environment. Essentially, the system lost some information to the environment, and this process can be modeled by this kind of expression here. I mean, if you have seen this expression before, you see that this is not just the Krauss operators. Okay, so this describes the non-unitary evolution of the system. You have a two-level system coupled to an environment, and then the system lost some information to the environment. So what happens with our geometric picture? Well, the initial state of the system is given by this sphere. But since the system lost information to the environment, the system is, let's say, somehow compressed to this object here, okay? So that is let's say, the geometric picture of our non-unitary evolution. Essentially, we have an open quantum system, and this open quantum system is modeled by these Krauss operators, okay? And these Krauss operators depend on this parameter lambda, and this lambda depend on time in this way. Okay. And after playing with the math, we can show that the quantum speed limit depends on these quantities. Well, here I have this quantum Fisher information, and here I have this function Q that is related to the coherences of the instantaneous state of the system regarding some basis. So we see that these functions should be equal to 0 for some initial parameters. I mean, since I parameterize the initial state of the system on the Bloch sphere, this state depends on some radius of this sphere, which is this rho naught, depend on this angle theta naught, and this angle phi naught. So for some initial parameters, for example, some theta not equal to 0 or pi, these quantities should be equal to 0. So what is our problem? Is to discuss this quantum speed limit time. So playing with the math, we can calculate analytically the expressions that appears in the inequality that I presented you before. Well, here I have the length of any path connecting the initial and the final state of the system, which is given here when I choose this function related to the quantum Fisher information. And here I have the geodesic length of the length of the geodesic path connecting initial and final states. And here I have the same thing, but choosing the Wigner-Yanassi information. So, well, these functions are quite complicated. Here we have this elliptic integral, and just look into these expressions. I think we cannot learn much more. And then to conclude, I have these plots here, and the plots show the length of the path connecting initial and final states. Here in these two panels here, I have the figure of merit. You can see that this function delta that I showed you before approaches 0 for a given function f that I choose it before. I mean, if I choose the information theoretic quantifier given by the Wigner-Yanassi information, I see that for some regions of this parameter gamma of tau, the system evolves faster than the evolution associated by the information theoretic quantifier related to the Fisher information. Well, that's the point. I mean, the main message is the following. Depending on the way in which I choose to distinguish the two states, the initial and the final states of the system, I might find two different results for the figure of merit. I mean, the system might evolve faster in some way in detriment of the other way. I mean, by using this Wigner and Askew information instead of using this quantum Fisher information. And here we have a more clear situation, because if you see for this range of parameters gamma of tau here, when this gamma of t is small, we see that the inequality is saturated. I mean, this figure of merit approaches zero more faster than using the quantum Fisher information. So, of course, these depend on the initial states of the system. I think I do not have more time to discuss the details about it. But the point is, you can play with the parameters of the initial state. I mean, I have parameterized the initial state of the system on the block sphere. So if I play with the radius of this sphere, if I play with the polar angle of this sphere and the azimuthal angle of this sphere, I mean, these angles theta and phi, I can see some regions in which the system evolves more faster. So in this way, we are proving that the coherences of the initial state also plays a role on this evolution. We can find some faster evolutions with some attainable initial states that exhibit some coherence. And finally, of course, we have some situations in which the systems also follow the geodesic path connecting the initial and final system. And we obtain this with some particular parameterizations of the initial state. I mean, for any radius of the block sphere, I mean, for any mixed state, since this angle theta naught is equal to zero, I mean, you choose any state on the north pole of the sphere, the system always follow a geodesic path connecting initial and final states. So in conclusion, we have obtained a geometric approach to address this quantum speed limit time. I mean, this ultimate bound imposed by quantum mechanics. I mean, I hope I have convinced you that this quantum mechanics impose some threshold on this time of evolution. We do not have an equality for this time. We do not have a time energy uncertainty relation. We have a kind of threshold for this time of evolution. And since we do not have a Hermitian operator related to time, we need to analyze the problem more carefully. So our formulation is unified. I mean, it works for both closed and open quantum systems. And we see, I mean, unfortunately, I did not have so much time to address carefully the role of the coherences and populations on the QSL, but this is one of our main results. And essentially, coherence can speed up the evolution. I mean, by changing these parameters, rho naught and theta naught, essentially we cover all the possible states of the system along the block sphere, not just on the surface of the sphere, but inside the surface, because we can change the radius of this sphere. And of course, by doing that, we are changing the coherences of the initial state of the system. We can speed up the evolution. So if the initial system exhibits some coherence, we can find some faster evolution. If you compare a given system described initially by any state that has no coherence. And of course, there are a lot of applications of these results. I mean, we may find some applications in quantum thermodynamics, quantum metrology. Quantum metrology, because the point is to estimate some parameter, some phase encoded on the system, at least some encoded locally on the system. And of course, you can understand that this quantum phase is nothing but the time. And then estimating time is more or less similar to estimate some quantum phase in some metrological protocol. And these results, of course, should find some applications in quantum control and, of course, in the processing of quantum information. If you have more, if you want to see more details, please see these papers. And with that, I would like to thank you. Thank you for listening. And if you have some questions, I will try my best. And here I have my email. If you have some questions, you can contact me. So thank you.
Thank you very much, Diego, by your nice talk. Are there any questions? Come forward, please.
Hello, thank you for the nice talk. I was wondering, it's more of a curiosity, have you done this analysis, or have you considered the analysis with the generalized quantum operations like quantum processes, quantum comps, and do the same analysis like that of a manifold, and considering the space in between operations?
Well, I'm afraid not understood precisely your question, but well, you can use this approach to investigate, in principle, any quantum operation. I mean, as I told you before, we can consider unitary quantum operations. I mean, suppose you have some quantum channel in which you do some operations that are mainly described by unitary operators. So somehow you have a closed quantum system. You can apply these results in this case. If you have an open quantum system, and when I say an open quantum system, maybe I should be careful about this, because I have presented you some example about this open quantum system in the view of these Krauss operators. Essentially, you have a quantum channel, and by doing some operations, the system might lose some information, and you can model these operations in this quantum channel by using these Krauss operators. Of course, there's some connection of this approach and the so-called master equation approach. And this master equation approach is a general setting. You can have any kind of jump operators, I mean the Lindblad operators. So in principle, depending on the open quantum system, you can construct these Lindblad operators, and you have this master equation, and by solving this master equation, or at least knowing the state of the system at some time t, you diagonalize the state of the system, you play with the math that I showed you before, and then you are in principle able to do this discussion to find out this time of evolution. The point is, if you increase the size of the system, this could be very difficult, because well, I have presented you the case of a two-level system, a qubit. But for example, if you consider a string of qubits, let's say a multi-particle system that locally is described, the local subspace has dimension 2, for example, a multi-particle system with dimension 2 to the power n. Suppose you have a multi-particle systems of n particles. Well, in this case, the solution of this problem could be quite complicated, and analytical expressions should be difficult. And then, of course, you can do this numerically with the precision, the best possible precision. My answer to your question, and I am not sure if I am answering your question precisely, is yes, we can consider in principle any state of finite dimension, of course, that involves some given dynamics, being unitary or non-unitary. I mean, being a closed quantum system or being an open quantum system. Okay.
I meant quantum operations. You say like open quantum systems would be described by Krauss operators. It would be a CP trace no increase in operation.
Exactly.
Okay.
When I say cross operators, I mean this quantum operation is a CPTP operator, a completely positive and tracing preserving operation. I mean, for each time t, the state of the system is normalized to the unity. If you are asking this, that's the point.
So
and this cross operator, of course, fulfill some let's say resolution to the unity, this closing property of cross operators. I mean, this quantum operation can be the general the most general possible, not just the, let's say, the unital operations. That's the point.
Thank you.
You're welcome.
Hi, Diego.
Hi.
So my question for you is, can you use this quantum speed limit to build or to construct a quantum discord measure?
Well, maybe yes, because when you say quantum discord measures, these quantities also depend on this, let's say, this whole family of information theoretic quantifiers, and of course, when you say quantum discord, you try to characterize correlations beyond entanglement, correlations older than entanglement. So I think yes, I never thought about it, but you can think about this problem in this way. I mean, you can search for those initial states that present some correlations, and then try to describe this this minimum time of evolution. I mean, let's say, suppose you have a G8Z initial state or a Werner state, and then you play this math. I mean, you of course you have the initial state. You have the system, the multi-particle system described by one of these two states. You evolve this state with some dynamics, and then you calculate this time of evolution. And then you try to understand what happens with this time when the system is when the initial state of the system is correlated. And somehow this have been done, and the people just concluded that entanglement promotes some speed up of the evolution. But I am not sure that people have somehow classified the possible ways to characterize the quantum discord and relate it to this with the quantum speed limit. Maybe it can be done. I am not sure.
Okay.
It's a nice, in each case, it's a nice question.
Oh, okay. Thank you.
Hello, Diego. I have a few questions, actually. You commented that you achieved a speed up when using coherence.
Yes.
Do you need to use all the coherence of the system to achieve that speed up? And can you do you observe some speed up when going from a low coherence state to a high coherence state?
Well, this using this framework, I think you are not able to classify this, but I think this can be done if you introduce some technique related to the concept called coherence orders. Because, of course, the point is you can write down, for some state described in a multi-particle system, you can write down the density matrix, and you can decompose this density matrix into some subspaces, and each subspace is related to some, let's say, some projector. Is not exactly the case, but somehow is the case. And then if you keep track on these projectors and each contribution of these projectors, and I mean each projector should be labeled with some quantum number, with some, let's say, some number m. And then I think you'll be able to conclude that for what kind of coherence order, what kind of subspace of this decomposition, this general decomposition, promotes this speedup. Of course, in this formulation, just to show you, let me show you. In this formulation, what matters here is this contribution. I mean, here I have this quantities A, J, L, which is related to these matrix elements. Well, here this J and L essentially are the eigen vectors of the initial state of the system, and then you take this time derivative. This can be written in another way, but just to keep the expressions here. Here we have some information about the coherences of the instantaneous state regarding to this basis. But of course, here we need to take in account all these coherences. That's the point. Your question is a good question because you are asking about keeping track of each contribution of coherences labeled by these quantum numbers, these coherence orders, and then answer this question of the speed limit time. I mean, for each kind of coherence order, you should have some speed up. That's a nice question, and I to be honest, I think it had not been addressed until now, but it's nice.
Thank you. And I have another question, is that when comparing the same evolution in a closed system and in an open system, do you observe a speed up due to the presence of noise in the open system?
Yes, essentially essentially all the information about the noise is if you think about this amplitude damping, the information about the noise is encoded here in this Krauss operator. Well, this time of evolution, the results depend on this gamma. Essentially, this is related to the dissipation, if you want to think about this way. But our conclusion mostly depend on the initial parameters of the system. But of course, there is some deep connection on these Krauss operators and the initial state of the system. And to understand this point better, you can change the quantum channel. I mean, here we have considered the amplitude damping, but you can consider the phase damping. We can take in account different quantum channels, for example, the Pauli channels, and then investigate what happens with this figure of merit here. I have the results for the phase damping, and we see that for some parameters, rho naught, theta naught, phi naught, I mean, for some initial states, the Fisher information is better than this Wigner and Askew information to answer this problem of speed limit time. What I mean with this? I mean that the Fisher information gives you the answer to this problem instead of this Wigner and Askew information. But for this amplitude damping, we clearly see that the Wigner and Askew information is the information theoretic quantifier to distinguish two quantum states that gives you let's say, the answer to this faster evolution. Behind of these technical details, the message is you have the space of quantum states, and to distinguish two states, you introduce some metric. You introduce some, let's say, some inner product. By changing this inner product, I mean, by changing the way in which you distinguish two quantum states, you can see that the system evolves faster in some for some information theoretic quantifier than the older one. Of course, the nature does not care about it, and of course you should compare this with some experiment, and you may find out some experimental papers trying to address this problem. But to the best of my knowledge, I think this is at least an experimental level. There's a huge gap to fill in this subject.
Thank you, Diego.
You're welcome.
Are there any more questions? Please come forward.
Hello, Diego. Firstly, thanks for the very interesting presentation. So you present results for non-relativistic regime, and I would like to know if it's possible somehow approach this problem in a relativistic regime, considering the Dirac equation or something like this.
Yes, nice question. Yes, and the answer is yes. And if I remember, this have been partially done by some colleagues. One of them is Eduardo Duzioni. I do not have, unfortunately, I do not have the reference here, but it has been done. And the point is you need to understand what is the behavior of the dynamics in the context, in the relativistic context. Well, in the behind of this nice words of closed quantum system, unitary evolution, we have Schrödinger equation. But in the context of, well, in the relativistic realm, we will have the Dirac equation. And this is more complicated because we have the spin and we have the spinors. And, but it can be done. As far as I know, they did not have applied this framework to discuss the problem. They have considered a different framework, but they have nice results regarding this subject. I mean, the relativistic version of the problem. And I am not sure. Maybe I'm saying something wrong, but they have some experimental results for some given system. But it can be done, and it was partially done in these works. But honestly, I think there is much more to be done in this subject.
Yes, thank you.
Hello, Diego. I'm sorry if I didn't understood quite correctly, but have you addressed the way that you put these constraints on this function that you're showing there? There was one of my questions.
Well, if I correctly understood the point, well, let us just comment this. Well, these functions, well, this is related to this theorem. I will not go into the technical details of this function f. Essentially, these functions have some particular properties that I will not show in the details here. The main message here, you can choose any function inside this blue region here.
Oh yeah, no, I understood that.
Yeah.
My question was more about how you define these constraints.
Okay. No. This is well, this is related to this theorem, and the point is there is a family of functions. There is a function analysis. There's a you may find these constraints in a paper by Dennis Petze. I am not sure about the name of the other authors, but I can send you the reference. If you are interested in, please just write an email. I can send you. But because the point is, this is a technical detail. I do not have this on the slides here. But there is some. Well, just to conclude, there is some function analysis. There is let's say a more deeper analysis in the mathematical level. And these mathematicians have cared a lot about these functions, and we know what kind of functions fits inside this region, and we also know why this function f max u is here, and we know why there is some minimum function f min of u here. It can be done, but it requires some, let's say, some technical work to check these properties of these functions.
Okay.
It can be done.
Okay. And another question is, if I understood correctly, the manifold in which the states are defined is problem is dependent on the problem that you're facing, right? That's
Yes.
the question.
Well, essentially, the manifold is the manifold of the quantum states. And of course, this manifold is related to the properties of these quantum states, because here we have states that fulfill some constraints. Well, the states are normalized to the unity. Well, technically, the trace of the density matrix is equal to 1. The density matrix is positive semi-definite. Essentially, the eigenvalues of this operator should be positive, greater than 0. And if you sum all of these eigenvalues, you should obtain 1. I mean, somehow you have some probability conservation. And of course, this initial state is a Hermitian operator. So by applying these 3 constraints, you have this you have some structure of this manifold that the mathematicians call the if I am not wrong, the positive cone of the quantum states.
Yeah.
So
no, that's enough. I got a little bit confused by this image. I was not sure if the states were defined in the tangent plane or in the surface of the manifold.
No. Well, here I just have a depiction. Well, just take this as a depiction. It's not the precise.
I got a little bit confused by this image. That's why I asked. But thank you.
Welcome.
Okay. Due to time issues, I'm sorry, but we will not be able to take any additional questions. So if you have an additional question, please write that to Diego. We can provide his email. And let us thank you again, Diego, by the nice talk.
Thank you, all of you. Thank you for the organizers.
And I have 2 reminders for you. The first one is that tomorrow, after the morning talks, we will be hosting a lunch, and I hope you can join us. And there will be a trip happening on Sunday. And if you are interested, please.
Eu que agradeço. Até uma próxima. Desculpa pelo barulho de fundo aí. Tinha umas crianças gritando aqui.
Não, tranquilo. Obrigadão.
Obrigado. Tchau, tchau.
Obrigado. Boa noite. Tchau, tchau.
Boa noite.
Sorry? Yes. Oh, sorry, I mixed it up. So there will be lunch tomorrow, and there will be a trip on Sunday. No, so I messed up. There will be no morning talks. Yeah. Yes. I believe it will be.
Do notebook, por favor.
Ô Thalita, alô.